There's a finish line in the universe that nothing can cross, the speed of light. But what if you didn't have to cross it? What if you could fold space, punch a hole through reality, or ride a wave in the fabric of space-time itself? These aren't science fiction concepts, they are real physics, impossibly difficult, but not impossible. What would it actually take to cheat light speed and travel faster than physics says we can? If you're fascinated by the cosmos, make sure to hit that subscribe button. Now let's get started. What makes light so special? The answer lies in what happens as you accelerate. Let's say you're in a spacecraft and you keep firing your engines, going faster and faster. According to Newton, you should just keep accelerating indefinitely, but Einstein showed that something bizarre happens instead. As you approach the speed of light, three things occur that stop you from ever reaching it. First, your mass increases. Not your physical size, your inertial mass, the resistance you have to being pushed. The closer you get to light speed, the more massive you become, which means you need more and more energy to accelerate further. Second, time slows down for you relative to the outside universe. If you could somehow reach 99% of light speed and travel to a star 10 light years away, you might experience the journey as lasting just over a year. But when you arrive, more than 10 years will have passed for everyone else. Time itself becomes elastic. Third, and most dramatically, lengths contract in your direction of motion. The universe literally squashes in front of you. At high enough speeds, the distance between stars would appear to shrink, making your subjective journey shorter even as outside observers see you taking years to arrive. These aren't just mathematical quirks. They're real effects that have been measured countless times with particle accelerators, atomic clocks on airplanes, and GPS satellites orbiting Earth. Time dilation, mass increase, and length contraction are facts of nature. And here's the kicker. As you approach the speed of light, these effects become infinite. Your mass would become infinite, requiring infinite energy to accelerate further. Time would stop completely. Length would contract to zero. The math doesn't just say it's hard to reach light speed. It says it's impossible. The universe has built an impenetrable wall at 299,792 kilometers per second. But wait, there's more to this story, and it gets even stranger. Light itself doesn't experience time. Think about that for a moment. A photon emitted from a distant galaxy billions of years ago, from our perspective, experienced no time at all during its journey. From the photon's point of view, if it could have one, it was created and absorbed in the same instant. The entire history of the universe, billions of years of cosmic evolution, happens in zero time for light. This is why light can travel at light speed, but nothing else can. Photons have no rest mass. They're pure energy, and they must travel at this cosmic speed limit. Anything with mass, on the other hand, can never reach it. So here we are, trapped. We're made of matter, composed of particles with mass, descendants of ancient stardust that formed in the hearts of long-dead stars. Our atoms, our molecules, our very existence is bound by this universal rule. We are forever barred from reaching the speed that would let us explore the galaxy in a human lifetime. Or are we? Because here's where the story takes an incredible turn. Einstein didn't just give us special relativity. A decade later, in 1915, he published his general theory of relativity, which describes how gravity works, and buried in those equations, physicists have found something remarkable, a potential loophole. General relativity tells us that space-time isn't rigid. It can bend, stretch, and warp. Massive objects like stars and planets create curves in space-time, and we experience those curves as gravity. Earth orbits the Sun not because of some invisible force pulling on it, but because the Sun's mass warps space-time, and Earth follows the straightest possible path through that curved geometry. Now here's the crucial insight. Special relativity says you can't move through space faster than light. But general relativity says nothing about how fast space itself can move. Think of it this way. Imagine you're standing on a moving walkway at an airport. You can't walk faster than your maximum walking speed. That's your personal speed limit. But if the walkway itself is moving, you can travel faster than you could walk alone, even though you're not breaking your walking speed limit. The ground beneath you is doing the extra work. Space-time can do something similar. While you can't move through space faster than light, space itself has no such restriction. And if you could somehow manipulate space-time, compress it in front of you and expand it behind you, you could surf on a wave of warped geometry, carried along faster than light without ever locally breaking the light barrier. This isn't science fiction. This is a legitimate consequence of Einstein's equations. The question isn't whether it's theoretically possible. The question is whether we can actually do it. And that brings us to one of the most famous ideas in theoretical physics, the Alcubierre warp drive. In 1994, a Mexican physicist named Miguel Alcubierre published a paper that sent ripples through the scientific community. He'd found a solution to Einstein's field equations that described exactly this kind of space-time manipulation, a way to create a warp bubble that could carry a spacecraft faster than light. Here's how it works. Imagine you're inside a bubble of normal, flat space-time. This is your protective cocoon. Outside the bubble, space-time is being dramatically warped. In front of your ship, space contracts, bringing your destination closer. Behind your ship, space expands, pushing your starting point further away. The bubble itself, carrying you along, moves through the surrounding space faster than light. But, and this is crucial, you're not actually moving through space at all. You're sitting still inside your bubble while space-time moves around you. From your perspective, you're not accelerating. You feel no forces. You could be floating weightless, sipping coffee, while outside the bubble, space is being twisted into impossible geometries. If you've ever watched Star Trek, this might sound familiar, and you'd be right. Alcubierre was directly inspired by the show's warp drive concept. He wanted to see if such a thing could exist within real physics, and astonishingly, he found that it could. The Alcubierre metric, the mathematical description of this warped space-time, is a valid solution to Einstein's equations. It doesn't violate relativity because nothing is actually moving faster than light through space. Space itself is doing all the work. But before you start celebrating, before you imagine cruising to Alpha Centauri next weekend, there's a catch. Actually, there are several catches, and they're enormous. The first problem is energy. To create the Alcubierre warp bubble as originally conceived, you would need negative energy. Not just a little bit. We're talking about amounts equivalent to the total mass energy of Jupiter, or in some calculations, the entire visible universe. Now, what is negative energy? It's not antimatter. That has positive energy. Negative energy is something even more exotic, a form of energy that would have a repulsive gravitational effect. In quantum field theory, negative energy can exist in tiny amounts under very specific conditions, like in the Casimir effect, where two metal plates placed extremely close together in a vacuum experience a tiny attractive force caused by negative energy density between them. But we're talking about microscopic effects in laboratory conditions. Scaling that up to wrap a spacecraft in a bubble of negative energy, trillions upon trillions of times stronger. That's not just difficult. With our current understanding, it seems physically impossible. And that's not the only problem. Even if you could create the warp bubble, how would you steer it? How would you start and stop it? The Alcubierre solution describes a constant velocity bubble moving through space, but it doesn't explain how you'd create it in the first place or how you'd change its trajectory. You'd be stuck on a straight line course, unable to navigate. There's also the causality problem. Faster than light travel, even if it doesn't locally violate special relativity, opens the door to time travel paradoxes. If you can travel to a distant star faster than light and then travel back, you might arrive home before you left. This creates closed time-like curves, paths through space-time that loop back on themselves, leading to all the classic paradoxes that make physicists very uncomfortable. And then there's the practical issue of what happens when you turn off the warp drive. As you accelerate to superluminal speeds, any stray particles or photons you encounter would accumulate in the warp bubble's forward region, building up enormous amounts of energy. When you decelerate and the bubble collapses, all that energy would be released in a catastrophic burst of radiation that could sterilize your destination. You'd arrive at an alien world just in time to incinerate it. These problems are so severe that for years after Alcubierre's paper, most physicists dismissed warp drives as a fun mathematical curiosity, but not something we'd ever build. The universe had given us a loophole, but the price of exploiting it seemed impossibly high. Yet science doesn't stand still, and over the past few decades, something remarkable has happened. Researchers haven't given up. Instead, they've been steadily chipping away at these problems, finding new approaches, refining the mathematics, and discovering that the picture is more nuanced than we thought. If you want to understand just how brutal the challenges of interstellar travel really are, even without trying to exceed light speed, I'd recommend checking out my video on the card above. It lays out all the staggering obstacles we'd face just trying to reach nearby stars at a fraction of light speed. But the fact that conventional interstellar travel is so difficult is exactly why warp drive research matters so much. The link is in the description and pinned on the comments, because here's what's changed. Scientists have found ways to dramatically reduce the energy requirements of warp drives. We're no longer talking about Jupiter masses or universe masses of negative energy. Some newer models suggest we might need only the mass energy of a large asteroid, still enormous, but at least theoretically imaginable for a sufficiently advanced civilization. In 2021, physicists Alexei Bobrik and Gianni Martir published a groundbreaking paper that reframed the entire conversation. They showed that you could classify warp drive spacetimes into different categories, and critically, some of these could be constructed using positive energy, the normal kind of energy we're familiar with. Now there's a trade-off. These positive energy warp drives can't exceed the speed of light. They're subluminal, meaning they'd still be slower than light, but they could still offer enormous advantages. Imagine a spacecraft that could maintain a constant high velocity, say 90% of light speed, without expending fuel for acceleration once the bubble was established. The occupants inside would experience minimal time dilation because they're in flat spacetime within the bubble. That's still extraordinary technology, even if it's not quite Star Trek. Even more exciting, in late 2025, researchers published a paper in the journal General Relativity and Gravitation describing what they called an irrotational warp drive, a design that significantly reduces the amount of negative energy needed. Compared to the original Alcubierre model, this new approach cuts the peak energy deficit by a factor of approximately 38. That's still exotic physics, still far beyond anything we can currently engineer, but it's moving in the right direction. The key innovation involves the geometry of the warp field itself. The original Alcubierre drive had what's called vorticity, a twisting, rotational quality to how spacetime was warped. This new design eliminates that rotation, creating a smoother, more efficient warp bubble. Think of it like the difference between a turbulent whirlpool and a smooth, laminar flow. Both move water, but one requires far less energy to maintain. What makes this particularly interesting is that the researchers didn't just propose this theoretically. they developed sophisticated computational tools to verify that their design satisfies Einstein's equations and calculated exactly how the stress-energy tensor, the mathematical object describing energy and momentum in space-time, behaves throughout the warp bubble. They confirmed that while negative energy is still required, it's confined to a thin shell around the bubble rather than filling the entire structure. This matters because if negative energy only needs to exist in a small region rather than permeating a massive volume, the total amount required drops dramatically. It's the difference between filling an Olympic swimming pool and coating it with a thin film. The engineering challenge is still monumental, but it's no longer physically absurd. Meanwhile, other researchers have been working on the steering problem. In 2026, a physicist named Antti published work showing how a warp drive could change velocity by using photon radiation, essentially a light-powered rocket effect. The spacecraft would emit powerful beams of light, and the recoil from that emission would change the bubble's trajectory. It's not as elegant as simply willing your ship to turn, but it demonstrates that warp drives don't have to be stuck on unchangeable trajectories. Lee's work revealed something profound about the physics involved. Any warp drive that wants to accelerate or change direction must radiate energy to do so. This is a consequence of fundamental conservation laws in general relativity. You can't steer through warped space-time for free. The universe demands payment in the form of radiated photons carrying momentum away from your ship. This connects to a deeper principle called the Bondi-Sachs formalism, which describes how energy and momentum behave at the edge of space-time at what physicists call null infinity, the boundary where light rays eventually end up. The formalism tells us that any asymptotically flat space-time, one that looks normal and flat far from the warp bubble, must conserve total momentum. Change your velocity, and you must send momentum somewhere else. The photon rocket satisfies this requirement. Now you might be wondering, even if we solve the energy problem and the steering problem, how would we actually build one of these things? Where would we even start? That's where the conversation gets really speculative, but also really interesting. Because if warp drives are going to transition from equations on paper to hardware in space, we need to understand the engineering pathway that could get us there. Let's start with negative energy. As I mentioned earlier, negative energy does exist in nature, just in vanishingly small amounts. The Casimir effect demonstrates this. When you place two uncharged, perfectly conducting plates in a vacuum just nanometers apart, quantum fluctuations of the electromagnetic field create a measurable force pushing the plates together. The region between the plates has negative energy density. This isn't just theory. The Casimir effect was first measured in 1948 and has been confirmed in increasingly precise experiments ever since. It's real, observable physics. The question is whether we could ever amplify it or generate similar negative energy effects on scales relevant to spacecraft. Some physicists have proposed using rotating cylinders or rings made of extremely dense matter. If you spin them fast enough, the dragging of space-time they create, an effect called frame dragging, which has been measured around Earth by satellites like Gravity Probe B, might produce regions of negative energy density. But the rotation speeds required are absurd, approaching the speed of light at the rim, and the structural integrity of any known material would fail catastrophically long before reaching those speeds. Others have suggested using quantum field effects in curved space-time. Near the event horizon of a black hole, for instance, quantum mechanics predicts the creation of particle-antiparticle pairs, with one falling into the hole and the other escaping. From certain perspectives, this creates negative energy inside the horizon. Could we somehow harness or replicate this effect? Maybe, But we're talking about building structures near black holes or creating artificial event horizons, which pushes the engineering challenge into the realm of Type 2 or Type 3 civilizations on the Kardashev scale, societies that can harness the energy of entire stars or galaxies. There's also the possibility that our understanding of quantum field theory is incomplete. String theory, loop quantum gravity, and other approaches to quantum gravity predict exotic effects that might allow for controllable negative energy under conditions we haven't yet explored. We're barely scratching the surface of quantum gravity physics. The energies required to probe these effects experimentally are far beyond what the Large Hadron Collider can achieve. But let's assume, for the sake of argument, that a sufficiently advanced civilization, maybe humanity in a few centuries, or an alien species that's been at this for millions of years, figures out how to generate and contain significant amounts of negative energy. What then? You'd need to shape it into the right geometry. The warp bubble isn't just a sphere of weird energy around your ship. It's a precisely engineered distortion of space-time with a specific mathematical profile. The warping needs to be strongest at the edges of the bubble and smoothly transition to flat space-time, both inside and outside. Getting this wrong could result in tidal forces that would tear your spacecraft apart or create instabilities that would cause the bubble to collapse. Think of it like building a magnetic bottle for fusion plasma. Plasma is incredibly hot and will destroy any material container it touches, so fusion reactors use powerful magnetic fields to confine the plasma without physical contact. Similarly, a warp bubble would need to be maintained by carefully controlled fields, gravitational or exotic energy fields, that keep the distortion stable and prevent it from dissipating or collapsing inward. This control system would need to respond in real time to any perturbations. Space isn't empty. Even in the depths of interstellar space, there are stray hydrogen atoms, cosmic rays, and photons from distant stars. Each of these carries energy and momentum. When they interact with your warp bubble, they'll perturb its structure. Your ship's systems would need to detect these perturbations and make constant, tiny adjustments to maintain the bubble's integrity. It's similar to how modern aircraft use fly-by-wire systems to make hundreds of tiny adjustments per second to keep the plane stable, except instead of adjusting control surfaces, you're adjusting the curvature of space-time itself. The computational requirements alone are staggering. And then there's the power source. Even if you've reduced the energy requirements from universe masses to asteroid masses, you still need to generate that energy. Where does it come from? Antimatter is often suggested. When matter and antimatter annihilate, they convert mass to energy with 100% efficiency, following Einstein's famous equation E=mc². For comparison, nuclear fusion converts less than 1% of mass to energy, and chemical rockets convert essentially none. Antimatter is the ultimate fuel. But here's the problem. We can make antimatter, but only in absolutely tiny quantities. CERN's particle accelerators have produced antimatter, but the total amount ever created by humanity would power a light bulb for a few minutes at best. Making enough antimatter to fuel a warp drive would require energy collection on a planetary or stellar scale, plus the technology to safely store antimatter, which annihilates instantly on contact with normal matter. Some proposals involve harvesting energy from black holes. The Penrose process, named after physicist Roger Penrose, describes how you could extract rotational energy from a spinning black hole by dropping matter into its ergosphere, a region just outside the event horizon where space-time is dragged around by the black hole's spin. In principle, you could get more energy out than you put in, with the black hole's rotation supplying the difference. Alternatively, a Dyson sphere, a megastructure that captures most or all of a star's energy output, could provide the power needed for warp drive operations. We're talking about civilizations capable of engineering on solar system scales, but if you're already contemplating warping space-time, you're already in that territory. There's also the intriguing possibility of vacuum energy. Quantum field theory tells us that even empty space isn't truly empty. It's filled with quantum fluctuations, virtual particles constantly popping in and out of existence. These fluctuations carry energy, a lot of it. Estimates suggest that the energy density of the quantum vacuum might be enormous, potentially infinite if certain calculations are taken at face value. Of course, if the vacuum energy were truly infinite, space-time would be curved into oblivion, and the universe wouldn't look anything like what we observe. The cosmological constant problem, the mismatch between theoretical predictions of vacuum energy and observations, is one of the deepest mysteries in physics. But if we could tap into even a tiny fraction of vacuum energy, it could power warp drives or other exotic propulsion systems. This is all highly speculative, of course. We don't know how to extract vacuum energy, or even if it's possible. But the point is that there are potential energy sources that could, in principle, meet the demands of warp drive technology if we can figure out how to harness them. Now let's talk about what it would actually be like to travel in a warp bubble, assuming we've solved all these engineering challenges. This is where the physics gets really counterintuitive and mind-bendingly strange. Inside the bubble, you'd experience normal physics. The interior of an ideal warp bubble is flat space-time, just like the space you're sitting in right now. There'd be no acceleration forces, no time dilation relative to your starting point, and no length contraction. You could float weightless or use artificial gravity from rotating sections of your ship, just like in any science fiction spacecraft, but looking outside the bubble would be bizarre. Light from the universe around you would be severely distorted by the warped space-time at the bubble's edge. Stars ahead of you would be blue-shifted, their light compressed to higher frequencies and energies, while stars behind you would be redshifted, their light stretched to lower frequencies at high enough warp speeds. The visual distortion would be extreme. The entire visible universe might compress into a bright ring around your ship, with everything ahead and behind you appearing in a narrow band. Some calculations suggest you might not be able to see anything outside the bubble at all, or only through carefully designed windows in the warp field that allow light to pass through without being completely scrambled. Communication with the outside universe would be problematic. Radio signals you transmit would be distorted by the warp bubble before escaping into normal space. Signals sent to you from outside would have to penetrate the bubble, potentially being red-shifted or blue-shifted beyond recognition. You might be effectively isolated during the journey, unable to receive messages from home or send updates on your progress. There's also the question of navigation. How do you know where you're going if you can't see properly? You'd need to rely on inertial guidance systems, pre-planned trajectories, and faith in your calculations. Any deviation from your planned course, caused by gravitational fields from unseen stars or the cumulative effects of small errors, could send you wildly off target across interstellar distances. And then there's the arrival problem I mentioned earlier. As you travel at superluminal speeds, you're not just moving through empty space, you're encountering particles, hydrogen atoms, dust grains, cosmic rays, and every photon from every star in your path. Normally, these would pass by harmlessly or impact your ship with negligible energy, but when you're inside a warp bubble, these particles interact with the warped spacetime in complex ways. Some calculations suggest that particles entering the front of the warp bubble get trapped and accumulate in the warp field itself, unable to pass through to the rear. As you travel, you're essentially building up a growing cloud of high-energy particles carried along with you. When you decelerate and drop out of warp, all that accumulated energy gets released at once. Physicist William Clark, building on earlier work by others, calculated that this release could produce a beam of particles and radiation with energies comparable to the most violent cosmic ray events we've ever observed. Anything in front of your ship, planets, space stations, other spacecraft, would be hit with a devastating pulse that could sterilize surfaces or destroy electronics. This isn't just a minor engineering problem. It's a fundamental consequence of how warp drives interact with the environment. Some researchers have proposed solutions, like using magnetic fields to deflect charged particles around the bubble or designing the warp field geometry to allow particles to pass through rather than accumulate. But these fixes add complexity and might require additional exotic matter or energy. There's also a deeper, more philosophical issue that we need to address: causality and time travel. This is where faster-than-light travel starts to mess with the logical structure of space-time in unsettling ways. Einstein's relativity tells us that space and time are relative. Different observers moving at different velocities experience time passing at different rates and disagree about whether events happen simultaneously. This is fine as long as everyone is moving slower than light. The theory remains consistent, and cause always precedes effect. But introduce faster-than-light travel, and the situation becomes much more complicated. In certain reference frames, a faster-than-light journey from point A to point B could appear to arrive before it departed. If you then make a return trip, also faster than light, you could potentially arrive back home before you left, creating a closed time-like curve, a path through space-time that loops back on itself. This opens the door to grandfather paradoxes and other logical contradictions. Could you travel back and prevent your own departure? What happens to causality if effects can precede their causes? Most physicists find these paradoxes so troubling that they suspect the universe must have some mechanism, maybe not yet understood, that prevents them from occurring. One proposed resolution is the chronology protection conjecture, put forward by Stephen Hawking. He suggested that the laws of physics might somehow conspire to prevent the creation of closed time-like curves. Perhaps quantum effects would cause warp bubbles to become unstable if they tried to form time loops. Perhaps the energy requirements would become infinite precisely at the threshold where time travel becomes possible. We don't know for sure, but the universe seems to be consistent and logical, which suggests there's something stopping these paradoxes. Another possibility is that faster-than-light travel is possible, but only in very restricted ways that don't allow time travel. For instance, if warp drives can only be used between locations that have pre-existing warp infrastructure, something like a network of gates or beacons, then you couldn't use them to create paradoxes because you'd need to travel slower than light to set up the network in the first place. Think of it like a highway system. You can drive very fast on a highway, but someone had to build the highway first by traveling slowly over the terrain. Similarly, maybe warp drives require pre-positioned equipment at both ends of the journey, equipment that had to be transported there conventionally. This would preserve causality while still allowing rapid travel between established waypoints. This brings us to an important point about the broader context of warp drive research. We're not just asking whether faster-than-light travel is possible, we're probing the fundamental structure of space-time itself, testing the limits of general relativity, and exploring how quantum mechanics and gravity interact in extreme conditions. Every advance in warp drive theory teaches us something about the universe. When researchers discovered ways to reduce the energy requirements of warp bubbles, They did so by gaining deeper insights into how stress energy couples to space-time curvature. When they tackled the steering problem, they learned more about conservation laws in general relativity. When they analyzed how particles interact with warp fields, they pushed forward our understanding of quantum field theory in curved space-time. This is how science works. We reach for impossible goals, and even if we don't achieve them, we learn profound truths along the way. The Apollo program didn't just land humans on the moon. It revolutionized computing, telecommunications, materials science, and countless other fields. Warp drive research, even if it never produces a working spacecraft, is already deepening our understanding of the cosmos. And here's the thing, we're still in the early stages of this scientific journey. General relativity is just over a century old. Quantum mechanics is roughly the same age. We've only recently begun to seriously grapple with quantum gravity, and we're still struggling to reconcile these two pillars of modern physics. The standard model of particle physics has been spectacularly successful, predicting phenomena with incredible precision. Yet we know it's incomplete. It doesn't include gravity, it doesn't explain dark matter or dark energy, which together make up 95% of the universe's energy content. It doesn't tell us why the fundamental constants have the values they do, or why matter exists instead of being annihilated by antimatter in the early universe. We're like explorers who've mapped the coastlines but haven't ventured deep inland. We can see mountains in the distance, mysteries like quantum gravity, the nature of dark energy, the origin of mass, but we haven't climbed them yet. And when we do, when we develop a complete theory that unifies quantum mechanics and general relativity, we might discover that the rules are different from what we currently think. String theory, for instance, predicts the existence of extra-spatial dimensions beyond the three we experience. These dimensions are supposedly curled up at scales far too small to detect directly, but they could have profound effects on physics at high energies. Some string theory scenarios allow for shortcuts through higher dimensional space, a concept called a brain world that could enable faster-than-light travel without requiring exotic matter in our familiar three dimensions. Loop quantum gravity, an alternative approach to quantum gravity, describes spacetime as fundamentally discrete at the smallest scales woven from quantum threads called spin networks. In this picture, spacetime isn't smooth and continuous but granular, like a fabric with individual threads. How does warp drive physics work when spacetime itself is quantized? We don't know yet, but the answer might reveal new possibilities or new constraints. There are also wilder ideas. Some physicists have explored whether wormholes, tunnels through space-time connecting distant locations, could serve as shortcuts for interstellar travel. Einstein and Nathan Rosen described these Einstein-Rosen bridges mathematically back in 1935, though they didn't think of them as traversable. In 1988, physicists Kip Thorne and Michael Morris showed that wormholes could potentially be held open and made traversable if you threaded them with exotic matter possessing negative energy density. Sound familiar? The same ingredient needed for warp drives might also stabilize wormholes. A traversable wormhole would be like a cosmic subway tunnel. Enter one mouth in our solar system, walk a short distance through the throat, and emerge from the other mouth near Alpha Centauri. From your perspective, you've taken a shortcut through higher dimensional space-time, bypassing the vast distance in normal space. You haven't traveled faster than light locally. Inside the wormhole, you're always moving slower than light, but you've covered interstellar distances in far less time than light traveling through normal space would take. Of course, wormholes come with their own set of enormous problems. Natural wormholes, if they exist at all, would be microscopic, quantum-scale objects far too small for a spacecraft. Enlarging one to usable size and stabilizing it would require technology and energy on par with or exceeding what's needed for warp drives. And like warp drives, wormholes raise causality concerns. You could potentially use a wormhole to travel backward in time by manipulating the relative time dilation at the two mouths. Still, wormholes remain an active area of research. In 2022, physicists even performed a quantum simulation of a wormhole using Google's quantum computer, creating a simplified model that exhibited some wormhole-like behavior. It wasn't a real wormhole, and it couldn't be used for travel, but it demonstrated that these concepts are amenable to experimental and computational investigation. Another exotic possibility involves exploiting the expansion of space itself. We know that the universe is expanding, and that expansion is accelerating, driven by mysterious dark energy. Distant galaxies are receding from us faster than light, not because they're moving through space faster than light, but because the space between us and them is expanding. This is perfectly consistent with relativity. Space itself has no speed limit, so could we somehow harness this expansion? Could we create a localized region where space contracts in front of us and expands behind us, mimicking cosmic expansion on a small scale? This is essentially what the Alcubierre drive does, but thinking about it in terms of controlled space-time expansion might suggest new approaches or engineering pathways. Dark energy itself remains one of the great mysteries of modern cosmology. We observe its effects, the accelerating expansion of the universe, but we don't know what it is. Is it a property of space itself, a cosmological constant as Einstein once proposed? Is it a dynamic field, something that changes over time? Could it be a sign that general relativity needs modification on the largest scales? If we ever figure out the nature of dark energy, that knowledge might unlock new physics relevant to warp drives. Perhaps dark energy is related to the quantum vacuum energy I mentioned earlier. Perhaps it involves fields or particles we haven't discovered yet. Understanding it could reveal how to manipulate space-time expansion in controlled ways. There's also the question of what role consciousness and observation might play, if any. Quantum mechanics tells us that observation affects outcomes. Particles exist in superpositions of states until measured. This has led to endless debate about the role of the observer in quantum theory. Does this have any relevance to warp drives or space-time manipulation? Probably not directly. Quantum effects typically matter at microscopic scales, and space-time curvature is usually a macroscopic, classical phenomenon. But when you combine quantum mechanics with gravity, strange things can happen. Hawking radiation from black holes is a quantum effect that depends on the curvature of space-time. The early universe, when everything was compressed to quantum scales, requires quantum gravity to understand, so maybe, just maybe, there are quantum aspects to warp drive physics that we haven't considered yet. Perhaps creating and maintaining a warp bubble involves quantum coherence across macroscopic scales, similar to how Bose-Einstein condensates or superfluids exhibit quantum behavior at scales large enough to see. This is all speculation, of course, but it illustrates how interconnected these questions are. Warp drives aren't just about building a faster spaceship. They're about understanding the deepest nature of reality, time, space, matter, energy, and how they all fit together. Let's zoom out for a moment and consider the human side of this equation. Why do we care so much about faster-than-light travel? Why have scientists devoted decades to studying something that seems so impractical? Part of the answer is pure curiosity. We're a species of explorers. From the moment our ancestors climbed down from the trees and started walking upright on the African savanna, we've been driven to see what's over the next hill, across the next ocean, beyond the next horizon. That drive took us out of Africa and across the globe. It took us to the moon, and it compels us to dream of the stars. But there's more to it than curiosity. There's also survival. Earth won't last forever. Our sun is about halfway through its lifespan as a stable star. In roughly 5 billion years, it will exhaust its hydrogen fuel and begin fusing helium, expanding into a red giant that will likely engulf the inner planets, including Earth. Long before that, perhaps in just 1 billion years, increasing solar luminosity will make Earth uninhabitable, boiling away the oceans and turning our world into a lifeless desert like Venus. Even if we avoid natural disasters, there are other threats: asteroid impacts, supervolcano eruptions, gamma-ray bursts from distant supernovae, nearby supernova explosions, passing stars disrupting the Oort cloud and sending comets raining into the inner solar system. Any of these could devastate or even extinguish life on Earth. And that's not even considering risks we create ourselves: climate change, nuclear war, artificial intelligence gone wrong, engineered pandemics. The only way to guarantee the long-term survival of humanity and Earth-originated life is to become multiplanetary and eventually interstellar. We need to spread throughout the solar system and beyond, establishing self-sufficient colonies on other worlds. That way, no single catastrophe can wipe us all out. But here's the problem. Interstellar colonization without faster-than-light travel is almost impossibly difficult. The distances are so vast, the travel times so long that conventional approaches strain credibility. Even if we built generation ships, enormous spacecraft designed to support human populations for thousands of years, the social, psychological, and technical challenges would be staggering. Would people born aboard a generation ship who'd never known Earth and would never see the destination remain committed to the mission? Would the ship's systems remain functional for millennia without access to manufacturing facilities? Would genetic diversity remain sufficient to prevent inbreeding? Would social structures remain stable across dozens or hundreds of generations? Alternatively, we could use suspended animation or cryogenic freezing, sending colonists in a state of hibernation to be revived upon arrival. But we don't currently have reliable suspended animation technology, and even if we develop it, keeping people frozen for centuries or millennia presents immense technical challenges. What if the ship's systems fail? What if the destination turns out to be unsuitable? The colonists would have no way to turn back or adapt. Some have proposed using embryo space colonization, sending frozen embryos and artificial wombs to distant worlds, with AI systems raising the children after arrival. This solves some problems but creates others. Who programs the AI? What culture and values does it teach? Is it ethical to create humans who'll never know their biological parents or their species' homeworld? All of these approaches, generation ships, suspended animation, embryo colonization, are theoretically possible, but they're difficult, risky, and would take extraordinary commitment and resources. Faster-than-light travel would change everything. A journey that might take thousands of years at sublight speeds could potentially be completed in weeks or months with a warp drive. This isn't just about spreading humanity to the stars. It's about what kind of interstellar civilization we could build. Without faster-than-light travel, colonies would be isolated, cut off from Earth and each other by the vast gulfs of space and time. Communication would take years or decades, trade would be impossible, cultural exchange would be minimal, each colony would evolve independently, potentially diverging so much that they'd become effectively separate species. With faster-than-light travel, the galaxy could be connected. Ships could travel between stars, carrying people, goods, and ideas. Humanity could maintain cultural cohesion across light years. We could have a true interstellar civilization, not just scattered, isolated outposts struggling to survive. This vision has inspired countless science fiction stories, from Star Trek to Foundation to The Expanse. And while science fiction often gets the details wrong, it serves a vital purpose. It helps us imagine possible futures and inspires us to work toward the ones we find most appealing. But let's be honest about where we actually stand. Right now, in 2026, we don't have warp drives. We don't have antimatter power plants or Dyson spheres. We haven't detected negative energy outside laboratory conditions. We haven't unified quantum mechanics and general relativity. We're not even close to building a prototype warp bubble, even a tiny one. The fastest spacecraft we've ever built, the Parker Solar Probe, reaches speeds of about 192 kilometers per second at closest approach to the Sun, fast by human standards, but less than 0.1% of light speed. Voyager 1, our most distant spacecraft, is traveling at about 17 kilometers per second relative to the Sun. At that rate, it would take more than 73,000 years to reach Proxima Centauri. We're still learning to take our first steps beyond Earth. We've sent 12 humans to the Moon, the last in 1972, more than 50 years ago. We've never sent humans beyond low Earth orbit since then. Mars, the nearest planet we're seriously considering for human colonization, is at least several months away with current propulsion technology, and we haven't even attempted a crewed mission yet. So why talk about warp drives at all? Why spend time and mental energy on something so far beyond our current capabilities? Because history teaches us that today's impossibilities can become tomorrow's realities. In 1903, the Wright brothers achieved the first powered flight, staying aloft for 12 seconds and covering 37 meters. 66 years later, humans walked on the Moon. Just over a century after that first flight, we have passenger jets that routinely carry hundreds of people across oceans at near the speed of sound. In the early 20th century, splitting the atom was considered impossible by many scientists. Nuclear power plants didn't exist. Nuclear weapons were science fiction. Yet within decades, we'd not only split the atom, but harnessed its energy for both power generation and devastating weapons. Computers evolved even faster. The first electronic computers filled entire rooms and had less processing power than a modern calculator. Now we carry supercomputers in our pockets that connect us to a global network of information. What took decades to achieve in the 20th century might take years in the 21st as our tools and knowledge accelerate. So while warp drives seem impossibly far away, it's worth remembering that we're not at the end of scientific discovery. We're not even close. We're still in the early chapters of humanity's story, still figuring out how the universe works. Every generation discovers things the previous generation thought impossible. And the research matters now, even if applications are centuries away. When physicists probe the mathematics of warp drives, they're pushing the boundaries of general relativity. When they calculate energy requirements, they're advancing our understanding of quantum field theory. When they simulate warp bubble dynamics, they're developing computational techniques that have applications in other areas. Science is cumulative. Each small advance builds on previous work. A breakthrough in quantum gravity might not give us warp drives immediately, but it might enable new technologies we can't even imagine yet. Understanding exotic matter might lead to new materials or energy sources. Figuring out how to manipulate spacetime on tiny scales in laboratory conditions might, over centuries, scale up to practical applications. There's also value in having audacious goals. The Apollo program didn't just land humans on the Moon. It catalyzed enormous advances in computing, telecommunications, materials science, and engineering. It inspired a generation of scientists and engineers. It showed what humans could accomplish when we dream big and commit resources to achieving those dreams. Warp drive research serves a similar function. It challenges physicists to grapple with the most difficult problems in theoretical physics. It gives us something to aim for, a vision of what might be possible if we keep pushing forward. and it keeps alive the dream of exploring the cosmos, of not being confined forever to a single star system. Now let's talk about alternatives. Even if warp drives prove impossible, or remain beyond our reach for centuries, are there other ways we might achieve effective faster-than-light travel, or at least make interstellar journeys practical? One possibility I've already mentioned is wormholes. While they have many of the same challenges as warp drives, requiring exotic matter, raising causality issues, they're a distinct approach based on different solutions to Einstein's equations. Research into warp drives and wormholes often overlaps, and advances in one area can inform the other. Another approach involves bending the rules in different ways. What if, instead of moving faster than light through space, we could transmit information faster than light? This wouldn't help with physical travel, but it would revolutionize interstellar communication. Currently, if we sent a message to Proxima Centauri using radio waves or lasers, it would take 4.2 years to get there, and another 4.2 years to receive a reply. A conversation would take over 8 years per exchange, making real-time communication impossible. But if we could send information faster than light, through quantum entanglement, hypothetical tachyon particles, or some other mechanism, we could have real-time conversations across interstellar distances. Quantum entanglement is particularly intriguing. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance and was troubled by it, but experiments have repeatedly confirmed that entanglement is real. However, and this is crucial, you can't use entanglement to send information faster than light. When you measure an entangled particle, you get a random result. The other particle's measurement will be correlated with yours, but without sending a classical signal, which travels at light speed or slower. To compare measurements, you can't extract meaningful information. Quantum mechanics seems deliberately designed to prevent faster-than-light communication through entanglement. Still, this is based on our current understanding of quantum mechanics. Maybe there's a loophole we haven't found yet. Maybe a deeper theory will reveal ways to exploit quantum effects for faster-than-light communication. It's a long shot, but it's worth exploring. Another radical idea involves digitizing consciousness. If we could upload human minds to computers, we could transmit those patterns as data streams to distant stars, then reconstruct the minds in new bodies or simulated environments at the destination. The person wouldn't physically travel faster than light, they'd be disassembled at point A and reconstructed at point B, but subjectively it might feel instantaneous. This raises profound philosophical questions about identity and consciousness. Would the reconstructed person be you or a copy? If your original body remains intact, are there now two of you? What does personal identity mean when minds can be copied and transmitted like files? These aren't just philosophical puzzles, they have practical implications. If the reconstructed version is genuinely you, with your memories and personality, then maybe this is a valid form of travel. But if it's merely a copy while the original you dies, then it's more like creating a clone than traveling. Most people would hesitate to step into a machine that destroys their body while creating a copy elsewhere, even a perfect copy, yet our intuitions about identity might not be reliable. Every cell in your body is replaced over time. The atoms that make up your body today are not the same atoms that made it up 7 years ago. In a very real sense, you're already a different physical entity than you were in the past. Yet, you still consider yourself the same person because of continuity of consciousness and memory. So maybe continuity isn't as important as we think. Maybe what matters is the pattern, not the specific substrate. There's also the possibility of time dilation travel. While this doesn't allow faster-than-light travel in an absolute sense, it can make interstellar journeys feasible from the traveler's perspective through relativistic effects. If you accelerate a spacecraft to a significant fraction of light speed, say 99%, time dilation becomes extreme. For the travelers aboard the ship, time passes much more slowly relative to the universe outside. A journey that takes thousands of years from Earth's perspective might take only decades or even years for the crew. This is real physics, confirmed by countless experiments. Particles accelerated in colliders experience time dilation. Unstable particles that would normally decay in microseconds survive much longer because from their reference frame, less time has passed. GPS satellites have to correct for time dilation effects because time runs slightly faster in orbit than on Earth's surface, exactly as general relativity predicts. So we could, in principle, send humans to distant stars using relativistic rockets. The engineering challenges are enormous. You need vast amounts of energy to accelerate to such speeds, and you have to worry about collisions with interstellar dust and gas at velocities where even tiny particles carry devastating kinetic energy. But it's possible within known physics. The catch is that while the journey might feel short to the travelers, thousands of years would pass on Earth. Everyone they knew would be dead. Civilization might have changed beyond recognition. They'd be time travelers moving into the future, with no way to return to their own era. Some people might find this acceptable, pioneers willing to sacrifice connection to their time for the sake of exploring new worlds. Others would find it unbearable. There's also the problem of building the engines. Most realistic designs for relativistic spacecraft involve some form of fusion or antimatter propulsion, perhaps combined with laser or particle beam sails pushed by energy beamed from the solar system. These technologies are far beyond what we currently have, though they're at least theoretically possible without requiring exotic physics. The breakthrough Starship project, announced in 2016 by physicist Stephen Hawking and investor Yuri Milner, proposes using powerful Earth-based lasers to push tiny spacecraft, essentially computer chips with light sails, to 20% of light speed. At that velocity, they could reach Proxima Centauri in about 20 years plus 4 years for their signals to return to Earth. This wouldn't allow human travel, but it would let us send robotic probes to nearby stars within a human lifetime. Cameras and sensors could image exoplanets up close, analyze their atmospheres, and search for signs of life. It's an ambitious project with enormous technical challenges, but it's based on known physics and engineering that could plausibly be developed within decades. What makes Breakthrough Starship particularly interesting is that it's already spurring technological development. Researchers are working on developing light sail materials that can withstand the intense laser heating without vaporizing. They're designing miniaturized cameras and sensors that can fit on a gram-scale spacecraft. They're figuring out how to aim lasers precisely enough to hit a sail the size of a few meters from Earth to interstellar distances. Even if the project doesn't fully succeed, these advances will have applications elsewhere. Light sails could be used for propellant-free maneuvering within the solar system. Miniaturized sensors could enable vast fleets of small, cheap probes throughout the solar system. High-power laser systems could have applications in space debris removal or asteroid deflection. This illustrates an important principle. Pushing toward ambitious goals, even seemingly impossible ones, generates useful progress along the way. We don't have to reach the final goal to benefit from the journey. Now let's consider an even more speculative possibility, that we're thinking about this problem entirely wrong. What if interstellar travel isn't about building better engines or manipulating time, but about changing what we are? Evolution shaped humans for life on Earth at one standard gravity, breathing oxygen-rich air, eating organic food, reproducing sexually, and living for decades. These characteristics were adaptive in our ancestral environment, but they're not necessarily optimal for space travel. Imagine a post-human or transhuman species extensively modified through genetic engineering, cybernetic augmentation, or integration with artificial intelligence. Such beings might not need to breathe, might derive energy from radiation or directly from electricity, might experience time differently, or might exist partly or entirely as software running on distributed computational substrates. For such beings, the challenges of interstellar travel might look completely different. If you don't need to eat, breathe, or maintain a warm, pressurized environment, spacecraft can be much simpler and lighter. If you can enter a state of extremely slowed metabolism or run your consciousness at variable speeds, long journeys become less psychologically challenging. If you can back up your mind and transmit it as data, death becomes less final and distance less meaningful. This isn't comfortable for everyone to contemplate. It raises questions about what it means to be human, whether we'd want to modify ourselves so extensively, and whether the beings that result would still be us in any meaningful sense. But it's worth considering because it might be the path that actual interstellar civilizations, whether human or alien, ultimately take. We might also be thinking too narrowly about what travel means. Science fiction often depicts interstellar travel as analogous to ocean voyages. You get in a ship, travel through a medium, and arrive at a destination. But maybe interstellar expansion will look more like how life spreads on Earth. Life doesn't deliberately travel. Seeds blow on the wind, spores drift in water, bacteria hitch rides on meteors ejected from planets. The process is slow, undirected, and wasteful. Billions of seeds fail for every one that successfully colonizes new territory. But over geological time, it's extraordinarily effective. Maybe interstellar colonization will follow a similar pattern. We send millions of tiny, simple probes to nearby stars. Most fail, but a few succeed in establishing footholds, featuring facilities that can replicate themselves using local resources. These slowly build up infrastructure, eventually creating environments where biological life or uploaded minds can exist. Then they send out their own probes to more distant stars. This is the concept of self-replicating probes, sometimes called von Neumann probes, after mathematician John von Neumann, who studied self-replicating systems. With such probes, you could potentially colonize the entire galaxy in a few million years, even at sublight speeds, because the colonization wave expands exponentially as each new outpost sends out more probes. There are risks to this approach, most notably that self-replicating probes could become uncontrolled like a cancer spreading through the galaxy, consuming resources without creating anything of value. Science fiction often explores this nightmare scenario with berserker probes or grey goo scenarios where runaway replicators devour everything, but if designed carefully with appropriate safeguards and limitations, self-replicating probes could be a way to seed the galaxy with life and intelligence without requiring faster-than-light travel or even direct human involvement. The beings that eventually emerge at these distant outposts might be very different from us, shaped by their local environment and the long isolation from Earth, but they'd still be our descendants in a meaningful sense. This connects to a broader question: should we expect interstellar travel to be common in the universe? If it's possible, why don't we see evidence of other civilizations doing it? This is the famous Fermi paradox, named after physicist Enrico Fermi, who supposedly asked during a lunch conversation in 1950, "Where is everybody? The galaxy is billions of years old. Even at sublight speeds, a spacefaring civilization could colonize the entire galaxy in a few million years, a blink of an eye on cosmic timescales. So if intelligent life is common, we should see signs of it everywhere. Yet we don't. There are many proposed solutions to the Fermi paradox. Maybe intelligent life is extremely rare. Maybe civilizations tend to destroy themselves before achieving interstellar travel. Maybe they choose not to expand. Maybe they're here but hiding. Maybe we're living in a simulation and the simulators haven't bothered to populate the universe with other beings. Or maybe interstellar travel is genuinely hard. So hard that even civilizations far more advanced than us struggle with it or give up on it. Without faster-than-light travel, the economics might just not work out. The energy and resources required to send even a small probe to another star are enormous. The return on investment is unclear. Why spend vast resources exploring distant stars when you could use those same resources to build habitats in your own solar system? Our solar system alone could potentially support trillions of humans if we built rotating cylinder habitats, mined asteroids for materials, and used solar energy efficiently. The physicist Gerard O'Neill calculated in the 1970s that we could build vast space colonies, each housing thousands or millions of people in Earth-like conditions, using materials available in the asteroid belt. If that's the case, maybe most civilizations decide to stay home, building Dyson swarms and O'Neill cylinders rather than venturing into the vast darkness between stars. Interstellar space would remain mostly empty, with civilizations clustered around stars, content within their own systems. But I'd like to think we're more adventurous than that. Humans have always explored, even when it was dangerous and the practical benefits were unclear. We climbed mountains because they were there. We crossed oceans not knowing what lay on the other side. We went to the moon partly for geopolitical reasons, but also because it was an extraordinary thing to do, a testament to human capability and ambition. That same spirit, that curiosity and drive to explore, might compel us to reach for the stars, even if it's difficult and expensive. Not because it's profitable, but because it's meaningful, because it's our nature, because the alternative, staying confined to one star system forever, feels like giving up on something essential to who we are. And maybe, just maybe, we'll figure out how to make it easier. Maybe warp drives will work. Maybe wormholes can be stabilized. Maybe we'll discover new physics that opens doors we can't currently imagine. This brings us back to the question of what we should be doing now, today, to advance toward this future. We can't build warp drives yet, but we can invest in the foundational science that might eventually make them possible. First and foremost, we need to continue pushing forward on fundamental physics. We need a working theory of quantum gravity that successfully unifies general relativity and quantum mechanics. This is one of the greatest unsolved problems in physics, and solving it will require brilliant minds, substantial funding, and probably some revolutionary insights we haven't had yet. Several approaches are being pursued. String theory attempts to describe all particles and forces as different vibrational modes of tiny one-dimensional strings. It naturally incorporates gravity and has produced many profound mathematical insights, but it hasn't yet made testable predictions that distinguish it from other theories. Critics argue it's become untethered from experiment, more mathematical philosophy than physics. Loop quantum gravity takes a different approach, quantizing spacetime itself rather than treating it as a smooth background. It predicts that space is fundamentally discrete at the Planck scale, about 10 to the minus 35 meters, with reality built from quantum loops of gravitational field lines. This approach has produced some testable predictions about how light from distant gamma-ray bursts might be affected by quantum space-time structure, though results so far have been inconclusive. Other approaches include causal set theory, which treats space-time as a discrete set of events connected by causal relationships, asymptotically safe gravity, which attempts to make quantum field theory work for gravity without needing a fundamentally different framework, and emergent gravity theories, which suggest that gravity isn't fundamental but emerges from more basic quantum information processes. We don't know which, if any, of these approaches will succeed. We might need something entirely different, a paradigm shift as radical as the transition from Newtonian mechanics to relativity and quantum mechanics, but we won't figure it out without sustained research effort. This research requires significant investment. Fundamental physics isn't cheap. Experiments require particle accelerators, gravitational wave detectors, space-based observatories, and other expensive infrastructure. Theoretical work requires supporting universities, research institutes, and the scientists who work there. It requires training new generations of physicists through graduate programs and postdoctoral positions, yet in many countries, funding for basic science has stagnated or declined. Short-term thinking dominates, with governments and funding agencies demanding immediate practical applications. But fundamental physics doesn't work that way. The discoveries that transform civilization often come from research that seemed utterly impractical at the time. When Michael Faraday discovered electromagnetic induction in 1831, it was a curiosity with no obvious applications. When asked about the practical use of his discoveries, he supposedly replied, "What is the use of a newborn baby?" Yet his work laid the foundation for electric generators, transformers, and the entire electrical grid that powers modern civilization. Quantum mechanics seemed like abstract theory when it was developed in the early 20th century. Now it's the foundation for semiconductors, lasers, MRI machines, GPS systems, and the computers and smartphones we depend on daily. The economic value created by quantum mechanics is measured in trillions of dollars, all stemming from research that was initially purely theoretical. We need that same long-term vision for 21st century physics. We need to fund quantum gravity research, high-energy physics, gravitational wave astronomy, and dark matter dark energy studies, not because they'll produce commercial applications next year, but because they're expanding human knowledge in ways that might transform everything decades or centuries from now. Beyond fundamental physics, we need to invest in relevant engineering and technology development. Even if we can't build warp drives yet, we can work on components and capabilities that would be needed. Energy generation and storage is critical. Whether we're talking about warp drives, fusion rockets, or laser-pushed light sails, interstellar travel demands enormous amounts of energy. We need better solar panels, more efficient nuclear reactors, progress toward practical fusion power, and research into antimatter production and storage. Every advance in energy technology brings us closer to the power levels needed for serious spaceflight. Materials science is equally important. Spacecraft that travel at high fractions of light speed need materials that can withstand extreme temperatures, radiation, and impacts from interstellar particles. Warp bubbles, if they're possible, might require exotic materials with bizarre properties. Self-replicating probes need manufacturing systems that can process raw materials in space. We should continue developing nanotechnology, advanced composites, superconductors, and metamaterials with tailored properties. We should study how to manufacture in space using asteroid resources. We should work on 3D printing and additive manufacturing techniques that could enable self-replicating systems. Artificial intelligence and robotics will be essential for any interstellar mission. Human crews are fragile, resource-intensive, and limited by psychology and biology. AI systems could manage spacecraft for centuries-long journeys, repair damage, make decisions when communication with Earth is impossible, and operate scientific instruments. Advanced robotics could mine asteroids, build infrastructure, and explore alien environments. We're making rapid progress in AI, perhaps more rapid than in any other technological field. Modern machine learning systems can drive cars, diagnose diseases, translate languages, generate images and text, play complex games at superhuman levels, and increasingly handle cognitive tasks we thought required human intelligence. This progress shows no signs of slowing, but we need to be thoughtful about AI development. Systems that will operate autonomously for centuries need to be robust, safe, and aligned with human values. An AI running a generation ship can't malfunction or decide that humans are inconvenient. An AI managing a self-replicating probe system can't go rogue and become a threat. We need to solve alignment and safety problems before we entrust AI with missions we can't oversee or correct. We also need practical experience with spaceflight. Before attempting interstellar journeys, we should master our own solar system. We should establish permanent settlements on the Moon and Mars. We should mine asteroids. We should build large structures in space, space stations, rotating habitats, solar power satellites. Each of these projects teaches us how to live and work off Earth, developing the technologies and experience needed for more ambitious ventures. The Moon is an excellent testing ground. It's close enough that help from Earth is only a few days away, yet harsh enough that it forces us to develop robust life support systems, radiation shielding, and in-situ resource utilization. We can learn to extract oxygen from lunar regolith, manufacture building materials, grow food in artificial environments, and maintain human health in low gravity. Mars presents greater challenges but also greater opportunities. It has an atmosphere, even if thin and unbreathable. It has water ice. It has a day length similar to Earth's. It has enough gravity, about 38% of Earth's, that long-term health effects might be manageable, and it's far enough away, a journey measured in months rather than days, that Martian settlers will need to be self-sufficient. Establishing a permanent, self-sustaining settlement on Mars would be one of the greatest achievements in human history. It would prove that humans can become a multiplanetary species. It would create a backup for Earth's biosphere and civilization. And it would develop many of the technologies needed for interstellar colonization, closed-loop life support, radiation protection, local manufacturing, psychological resilience in isolated environments. Beyond Mars, there are the moons of the outer solar system. Europa, orbiting Jupiter, almost certainly has a global ocean beneath its icy crust, kept liquid by tidal heating. That ocean might harbor life, not intelligent aliens, but perhaps microbial organisms adapted to the dark, high-pressure environment. Discovering life on Europa, even simple life, would be one of the most profound discoveries in history. It would tell us that life isn't unique to Earth, that it can arise wherever conditions permit. Enceladus, a small moon of Saturn, has similar characteristics. Geysers shoot water from beneath its surface, and spacecraft have detected organic molecules in the plumes. Titan, Saturn's largest moon, has lakes and rivers of liquid methane and ethane, a thick nitrogen atmosphere, and complex organic chemistry. It's one of the most Earth-like environments in the solar system. Despite being utterly alien in detail, exploring these worlds would advance our understanding of life's possibilities. It would test our ability to operate robotic systems at great distances with long communication delays. And it would inspire people, showing that there are wonders in our own cosmic neighborhood worth discovering. But let's be honest, all of this, moon bases, Mars colonies, missions to the outer moons, while extraordinary, is still confined to our solar system. These are important steps, but they're not the final destination. The stars remain beyond reach with our current technology. So what's the realistic timeline? When might we actually achieve interstellar travel with or without faster-than-light capability? No one knows for certain, but we can make educated guesses based on the pace of scientific and technological progress. If history is any guide, we're both better and worse at predicting the future than we think. We often overestimate what can be achieved in the short term while underestimating what's possible in the long term. In 1968, the film 2001, A Space Odyssey depicted a future with permanent moon bases, commercial space stations, and missions to Jupiter, all by the year 2001. We didn't achieve any of that. Space progress slowed dramatically after Apollo, constrained by political will and budgets rather than technology. Yet that same era completely failed to predict the internet, smartphones, and social media, technologies that have transformed civilization more than moon bases would have. The future rarely unfolds as we expect. With that caveat, here's my speculation. Within the next few decades, say by 2050 or 2060, we'll likely have permanent human settlements on the Moon and Mars. We'll be mining asteroids and building substantial infrastructure in cislunar space. We might have achieved controlled fusion power, dramatically expanding our energy options. We'll have much more advanced AI and robotics. By 2100, we might be launching the first serious interstellar probes, perhaps something like breakthrough starshot, or perhaps small fusion-powered craft that can reach a few % of light speed. These would be robots, not crewed missions, but they'd represent humanity's first steps to other star systems. Crewed interstellar missions, if they use conventional propulsion, probably won't happen until the 22nd century at the earliest. We'll need more experience with long-duration spaceflight, better life support systems, and compelling reasons to send humans rather than machines. Perhaps we'll discover an Earth-like exoplanet close enough and interesting enough to justify the enormous expense and risk. As for faster-than-light travel, warp drives, wormholes, or something we haven't conceived yet, that's much harder to predict. It depends entirely on whether such things are possible, and we don't know that yet. If they're allowed by physics but require technology and energy far beyond our current capabilities, we might achieve them in a few centuries, perhaps by the 24th or 25th century. That would make Star Trek's timeline, warp drive invented in 2063 in the show's fictional history, optimistic but not absurdly so. If they require insights we won't gain until we have a complete theory of quantum gravity, which might take another century of theoretical work, plus additional centuries to develop practical applications, we might be looking at the year 3000 or beyond. And if they're simply impossible, if the universe fundamentally forbids faster-than-light travel to preserve causality, then we'll need to content ourselves with slower methods, and interstellar civilization, if it happens at all, will look very different from what science fiction depicts. If you are enjoying this journey, please subscribe to the channel. Your support means a lot. You'll be joining a community of curious minds who refuse to accept impossible as the final answer. Here's something crucial to understand. Even if faster-than-light travel proves impossible, that doesn't mean interstellar exploration is pointless or that we should give up on the dream. It just means we need to adjust our expectations and strategies. A civilization that masters its own solar system, builds vast orbital habitats, harnesses the sun's energy with Dyson swarms, and sends self-replicating probes to nearby stars might not resemble the galactic empires of science fiction, but it would still be extraordinary. It would still represent an enormous expansion of life and consciousness beyond Earth. It would still mean that humanity had overcome its cradle and taken its place among the stars, even if traveling between them took centuries rather than hours. There's also something to be said for patience and long-term thinking. Modern civilization is obsessed with speed and immediate results. We want instant communication, same-day delivery, quick returns on investment, but the cosmos operates on different timescales. Stars live for billions of years, galaxies evolve over cosmic epochs. Life on Earth took 4 billion years to produce beings capable of contemplating the universe. Maybe becoming truly spacefaring requires us to adopt a different temporal perspective. Maybe we need to think in terms of centuries and millennia rather than quarters and election cycles. Maybe we need to start projects that won't be completed in our lifetimes, whose benefits will be reaped by our descendants dozens of generations hence. This isn't how modern society typically operates, but it's how cathedrals were built in medieval Europe, projects spanning generations, with workers knowing they'd never see the completed structure. It's how we should think about climate change, making sacrifices now to protect people who won't be born for decades. And it's how we might need to think about interstellar exploration. Imagine a civilization that commits to a 1,000-year project, building and launching generation ships to a dozen nearby star systems. The first generation builds the infrastructure, the second generation constructs the ships, the third generation launches them. Generations 4 through 50 live and die aboard those ships, maintaining them, raising children who'll continue the journey. The 51st generation arrives at new worlds and begins the process of colonization. From our modern perspective, this seems almost unthinkably long-term. Would people stay committed to such a project? Would societies remain stable enough to see it through? Would the technology survive across centuries? But consider that many human institutions have persisted far longer than 1,000 years. The Catholic Church has existed for 2 millennia. Universities like Oxford and Cambridge have operated continuously for nearly a millennium. The Japanese imperial family claims an unbroken lineage spanning over 2,500 years. China's civilization has maintained continuity for thousands of years, despite dynasties rising and falling. So long-term projects aren't impossible for humans. We can maintain institutions, traditions, and commitments across many generations when we believe they're important enough. The challenge is creating that sense of importance and continuity around interstellar exploration. This is where culture, education, and inspiration matter. We need to tell stories about why the stars matter. We need to educate each generation about the cosmic context of human existence. We need to create a civilization that values exploration, discovery, and long-term thinking alongside immediate needs and comforts. Science fiction plays a role here. For all its sometimes loose relationship with actual physics, science fiction shapes how we imagine the future and what we think is worth striving for. Star Trek inspired multiple generations to pursue careers in science and engineering. The Mars trilogy by Kim Stanley Robinson influenced how people think about planetary colonization. The Expanse has made space visceral and real in ways that dry technical papers never could. We need more and better visions of humanity's future among the stars. We need stories that grapple honestly with the challenges while still conveying wonder and possibility. We need to show young people that the universe is vast and strange and full of mysteries worth exploring, and that they could be part of that exploration. But stories aren't enough. We also need visible progress. We need achievements that people can point to and say, "Look, we're actually doing this." The Apollo program did that for the 1960s generation. The images of humans walking on the moon, transmitted live to hundreds of millions of viewers, made space exploration real and immediate in a way that nothing before had done. We need similar moments for the 21st century. The first humans setting foot on Mars will be such a moment. The first detection of biosignatures in an exoplanet's atmosphere could be another. The first successful demonstration of a fusion reactor producing more energy than it consumes. The first asteroid mining operation returning precious metals to Earth. The first baby born in a permanent off-Earth settlement. These milestones matter not just for their practical significance, but for their psychological and cultural impact. They prove that humanity is still pushing forward, still reaching beyond what we've already achieved. They give people hope and purpose. They show that we're not confined to Earth forever, slowly depleting its resources and degrading its environment until we collapse. They show we have options, futures, possibilities. Now, let's talk about some of the more exotic and speculative ideas that occasionally appear in physics literature and science fiction. These are even more uncertain than warp drives, but they're worth mentioning because they illustrate just how strange and wonderful the universe might be. One concept is the possibility of parallel universes or alternate dimensions. Various interpretations of quantum mechanics and some versions of string theory suggest that our universe might be one of many, perhaps infinitely many, existing in parallel. The many worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957, suggests that every quantum measurement causes the universe to split into multiple branches, each representing a different outcome. If parallel universes exist and we could somehow access them, it might offer a form of travel that bypasses the normal constraints of space-time. You wouldn't fly from Earth to a distant star through normal space. Instead, you'd shift to a parallel universe where Earth analog is already close to the destination analog, then shift back. This sounds absurd, and there's no evidence it's possible, but it's the kind of creative thinking that sometimes leads to breakthroughs. Another concept involves manipulating higher dimensions. We experience 3 spatial dimensions and 1 time dimension, but some theories propose that additional dimensions exist, curled up at scales too small for us to perceive. If we could access these higher dimensions, space might have different properties. Distances that are vast in our 3-dimensional space might be short through higher dimensional shortcuts. This is somewhat analogous to how an ant walking on a garden hose experiences a 2-dimensional surface forward-backward along the hose and around its circumference. But from our 3-dimensional perspective, the hose is a 1-dimensional line, and we can take shortcuts the ant can't. Similarly, if higher dimensions exist, beings who could access them might find shortcuts through our space. String theory naturally incorporates extra dimensions, typically 6 or 7 beyond the 4 we experience, for a total of 10 or 11 dimensions. These extra dimensions are thought to be compactified, curled up into tiny shapes at each point in space. The specific shape and size of these compactified dimensions would determine the properties of particles and forces we observe. If we could somehow uncompactify these dimensions or move through them, the rules might change. But this is extraordinarily speculative. We have no evidence that extra dimensions exist, no idea how to access them if they do, and no understanding of what consequences that would have. Then there's the concept of manipulating the constants of physics. The universe is governed by fundamental constants: the speed of light, the gravitational constant, Planck's constant, the fine structure constant, and others. These constants determine how reality works. They set the maximum speed, the strength of forces, the behavior of quantum systems. But why do these constants have the specific values they do? We don't know. They might be truly fundamental, unchangeable features of reality, or they might be environmental, different in different regions of space or in different universes, selected by some process we don't understand. If the constants aren't truly constant, if they can vary or be manipulated, then changing them might change what's possible. Increasing the speed of light, even locally, would allow faster travel without technically exceeding light speed. Altering the gravitational constant might make it easier to manipulate space-time. These ideas venture into highly speculative territory, well beyond anything we can currently test or even model rigorously. There's also the possibility of utilizing black hole physics in clever ways. Black holes are regions where gravity is so intense that space-time curves back on itself, creating an event horizon from which nothing, not even light, can escape. They're perhaps the most extreme environments in the universe, and their physics is correspondingly exotic. Rotating black holes, described by the Kerr metric, have even stranger properties. They have an ergosphere, a region outside the event horizon where space-time is dragged along with the black hole's rotation. A spacecraft could potentially enter the ergosphere, dump unwanted matter or radiation, and escape with more energy than it came in with, extracting rotational energy from the black hole. This is called the Penrose process, named after physicist Roger Penrose. Even more speculatively, rotating black holes might contain wormhole-like structures or closed time-like curves that could theoretically allow travel to other regions of space or even other times. These solutions appear in the mathematics of general relativity, but whether they exist in physical reality is unclear. Even if they do, approaching a black hole closely enough to utilize these features would be extremely dangerous, requiring technology far beyond anything we currently have. Some physicists have even speculated about creating microscopic artificial black holes and using them for various purposes: energy generation, waste disposal, or space-time manipulation. But this would require concentrating enormous energy in tiny volumes, and we don't know if it's practically achievable or if quantum effects would prevent it. All of these ideas, parallel universes, higher dimensions, variable constants, black hole engineering, are highly speculative. Many physicists would say they're too speculative, venturing into untestable philosophy rather than science. But science has a history of what seemed impossible becoming routine. Transmutation of elements was medieval alchemy until nuclear physics made it real. Flying machines were fantasies until they weren't. Landing on the moon was science fiction until it was history. So, while we should maintain appropriate skepticism, we shouldn't completely dismiss ideas just because they seem wild. The universe is under no obligation to conform to our intuitions about what's reasonable. That said, we need to distinguish between different levels of speculation. Some ideas, like warp drives, are at least consistent with known physics, even if we don't know how to build them. Others, like parallel universe travel, have no known physical mechanism and are purely speculative. We should invest most of our resources in nearer-term, more plausible approaches while keeping an open mind about more exotic possibilities. Let's return to something more grounded. What should our priorities be right now, in the 2020s and beyond, if we want to make meaningful progress toward becoming an interstellar species? I'd argue we need to work on multiple fronts simultaneously: fundamental science, practical engineering, economic development, and cultural preparation. These aren't separate tracks, but interconnected efforts that reinforce each other. On the science front, we should prioritize research that could unlock new possibilities. Continue searching for a quantum theory of gravity. Support research groups working on string theory, loop quantum gravity, and alternative approaches. Fund particle accelerators and gravitational wave observatories that can probe physics at extreme energies and in extreme conditions. Even if these don't immediately lead to warp drives, they'll deepen our understanding of reality in ways that might eventually enable breakthrough technologies, expand exoplanet research. We've discovered thousands of planets around other stars, but we're only beginning to characterize them in detail. Next-generation telescopes, both ground-based and space-based, will be able to analyze exoplanet atmospheres, searching for biosignatures, chemical imbalances that suggest the presence of life. Finding life on other worlds, even microbial life, would be transformative. It would tell us whether we're alone or part of a living cosmos. Invest in propulsion physics, continue researching fusion drives, antimatter production and storage, laser sail technology. and other advanced propulsion concepts. Support experimental work on concepts like the Alcubierre drive, even though they currently seem impossible, because the process of trying to build them might reveal new physics or lead to unexpected breakthroughs. Study the interstellar medium. We need to understand what spacecraft will encounter between stars, the density of dust and gas, the radiation environment, the magnetic fields. Missions like Voyager and the upcoming Interstellar Probe will provide crucial data about the space beyond our solar system. On the engineering front, we need to develop practical capabilities. Perfect closed-loop life support systems. Any long-duration space mission needs to recycle air, water, and nutrients with minimal loss. We've made progress on the International Space Station, but we need systems that can operate for decades or centuries with minimal resupply. This means mastering bioregenerative systems, using plants and microorganisms to recycle waste into food, water, and breathable air. Develop in situ resource utilization. Rather than carrying everything from Earth, we need to manufacture what we need from materials found in space. This means extracting water from lunar or asteroid ice, producing oxygen from metal oxides in regolith, manufacturing building materials and propellant from local resources. Demonstrations like NASA's MOXIE experiment on Mars, which produces oxygen from the Martian atmosphere, are important proof-of-concept steps. Advent space nuclear power. Solar panels work well near the Sun, but they're inadequate for the outer solar system and useless for interstellar missions. We need compact, reliable nuclear reactors that can provide power for decades. NASA's Kilopower project and similar efforts are developing small fission reactors suitable for space use. Eventually, we'll need fusion reactors, but fission can serve us in the nearer term. Master large-scale space manufacturing and construction. We need to learn how to build big structures in space, habitats, solar power arrays, spacecraft assembly facilities. This requires developing techniques for zero-gravity manufacturing, autonomous robotic construction, and joining materials in vacuum protect against radiation. Space beyond Earth's magnetic field is filled with radiation, solar particles, galactic cosmic rays, and high-energy particles from supernovae and other cosmic events. Long-term exposure causes cancer, damages organs, and degrades electronics. We need better shielding, perhaps using water, hydrogen-rich materials, or electromagnetic fields. We need medical countermeasures and better understanding of radiation biology. On the economic front, we need to make space activity sustainable, develop the space economy. Space needs to pay for itself, at least partially. This means commercial satellite services, space tourism, mining asteroids for valuable materials, manufacturing products that benefit from microgravity, and potentially solar power satellites beaming energy to Earth. The more economic activity occurs in space, the more infrastructure gets built, and the easier further expansion becomes. Reduce launch costs. SpaceX has already revolutionized spaceflight by developing reusable rockets that dramatically reduce the cost of reaching orbit. We need to continue this trend, making space access cheaper, more reliable, and more routine. Fully reusable launch vehicles, air-breathing hypersonic spacecraft, and eventually space elevators or orbital rings could make reaching orbit as economical as international air travel. Create markets for space products and services. Governments can jumpstart space activity through procurement, buying transportation services, purchasing data from space-based sensors, contracting for lunar or asteroid materials. As private companies see viable markets, investment flows in, accelerating development, establish property rights and legal frameworks. Space law is currently based on the Outer Space Treaty of 1967, which states that celestial bodies cannot be claimed by nations, but it's unclear how this applies to private entities, and ambiguity creates risk that discourages investment. We need international agreements that clarify property rights, resource ownership, and legal jurisdiction in space while preventing a free-for-all that could lead to conflict. On the cultural front, we need to prepare humanity psychologically and socially, improve scientific literacy. People need to understand the basics of astronomy, physics, and biology to appreciate why space exploration matters. They need to grasp the scales involved, how far away stars are, how long journeys take, how fragile Earth is in the cosmic context. Better science education at all levels is essential to foster long-term thinking. We live in a society focused on the immediate, the next quarterly earnings report, the next election cycle, the next social media trend. We need to cultivate the ability to think decades and centuries ahead, to value projects that won't pay off in our lifetimes, but will benefit our descendants. This requires changes in how we structure institutions, incentives, and cultural narratives, develop the psychology of deep space. Living in space, especially on long interstellar journeys, will be psychologically challenging. Isolation, confinement, distance from Earth, lack of natural environments, interpersonal conflicts, all of these affect mental health. We need to understand these challenges and develop countermeasures, crew selection criteria, habitat design that supports well-being, communication strategies, meaningful work, access to nature or nature analogues. Research in Antarctica, submarines, and analog habitats provides some insights, but we need more. Are the ethics of space colonization? Should we terraform Mars, potentially destroying any native life? Do we have a right to exploit asteroid resources? How do we govern space settlements? What rights do spaceborne children have? Who gets to go to space? And how do we prevent it from being only for the wealthy? These questions don't have easy answers, but we need to grapple with them before they become urgent. Build international cooperation. Space exploration works best as a collaborative endeavor. The International Space Station demonstrated that former Cold War adversaries could work together on complex long-term projects. We need to extend that cooperation, bringing more nations into space programs, sharing technology and data, and creating frameworks for joint missions to Mars, asteroids, and eventually other star systems. Competition has its place. It drove the space race. But for truly ambitious goals, cooperation multiplies capabilities. At the same time, we need to maintain healthy competition. Multiple nations and private companies pursuing space goals creates redundancy, generates diverse approaches, and accelerates progress through competitive pressure. The key is balancing cooperation and competition appropriately. There's also an important question about artificial intelligence's role in all of this. AI is advancing rapidly, and many experts believe we could develop artificial general intelligence, AI with human-level cognitive abilities across all domains, within the next few decades. Some predict superintelligence, AI vastly smarter than humans, could follow soon after. If we develop advanced AI before we achieve interstellar travel, it might change everything. AI could design better spacecraft, solve the physics problems we're stuck on, manage complex missions, or even be the explorers themselves. Von Neumann probes become much more plausible if they're controlled by sophisticated AI that can adapt, learn, and make complex decisions, but this introduces new concerns. Would AI explorers still represent humanity in a meaningful way? If we send AI to colonize the galaxy while biological humans stay near Earth, is that success or a form of obsolescence? And there are safety concerns. An AI probe that malfunctions or has poorly specified goals could cause enormous harm, especially if it's self-replicating. The relationship between biological intelligence and artificial intelligence might define the next few centuries. Perhaps we'll merge with AI through cybernetic augmentation, becoming post-biological beings with both organic and synthetic components. Perhaps we'll upload our minds into machines, becoming software that can be transmitted at light speed. Perhaps biological humans and AI will coexist as different but complementary forms of intelligence, each suited to different environments and tasks. Or perhaps AI development will stagnate short of human-level intelligence, and biological humans will remain the primary form of intelligence in the universe. We don't know yet, but the decisions we make about AI development now will shape what space exploration looks like in the future. Another factor to consider is life extension and human enhancement. If we can dramatically extend human lifespan through genetic engineering, nanotechnology, or other medical advances, it changes the calculus of interstellar travel. A journey that takes a century is much more palatable if you expect to live 500 years than if you'll be dead long before arrival. Research into aging is making real progress. We're beginning to understand the biological mechanisms that cause senescence, telomere shortening, mitochondrial dysfunction, cellular senescence, stem cell exhaustion, and others. Interventions that target these mechanisms have extended lifespan in laboratory animals. It's not certain whether these will translate to humans or how far lifespan can be extended, but the possibility is real. If we combine life extension with hibernation or suspended animation technologies, even longer journeys become feasible. You could sleep through decades of transit, aging slowly or not at all, waking when you reach your destination. Science fiction has explored this concept extensively, and while we don't have working suspended animation for humans yet, research on induced hypothermia and metabolic slowdown suggests it might eventually be possible. There's also the question of reproduction and child-rearing on long journeys or in space colonies. If we're sending generation ships to other stars, people will be born, live, and die aboard those ships. They'll need education, socialization, purpose, and opportunities. Creating societies that can function and thrive for generations in artificial environments is a massive challenge, perhaps as difficult as the engineering challenges. We might need to develop entirely new social structures adapted to space conditions. Traditional family structures might not work in small, isolated populations where genetic diversity is limited and everyone depends on everyone else. We might need new approaches to governance, conflict resolution, resource allocation, and cultural transmission. Some of this we can test in Earth-based analogues or on Moon and Mars colonies before attempting interstellar journeys. But there will inevitably be surprises, challenges we didn't anticipate. The first-generation ship crews will be pioneers not just physically but socially and culturally, creating new ways of being human. Now, let's consider some of the philosophical and existential questions that interstellar travel raises. These aren't just abstract musings. They affect how we think about the purpose and value of expanding beyond Earth. Why should we go to the stars at all? This is a fundamental question that deserves a serious answer. Space exploration is expensive, it's risky, it diverts resources that could address problems here on Earth: poverty, disease, climate change, inequality. So why do it? One answer is survival. Earth is fragile. Asteroid impacts, supervolcano eruptions, nuclear war, pandemics, runaway climate change. Any number of catastrophes could devastate or even end human civilization. As long as all of humanity lives on one planet, we're vulnerable to extinction from a single event. Establishing self-sustaining colonies elsewhere, on Mars in orbital habitats, eventually around other stars, creates redundancy. It ensures that no single catastrophe can end the human story. This is sometimes called the backup Earth argument, and it has merit. But it's not entirely satisfying. Establishing backup colonies is phenomenally expensive. For the cost of a Mars colony, we could build enormous asteroid defense systems, pandemic response capabilities, and climate change mitigation infrastructure here on Earth, addressing the threats directly rather than fleeing from them. A deeper answer involves growth and flourishing. Life on Earth has been expanding and diversifying for billions of years, filling every available niche, adapting to every environment. Expansion is what life does. Intelligence emerged from this process, giving us the capacity to expand not just through slow evolution, but through deliberate effort and technology. From this perspective, going to the stars isn't abandoning Earth, but fulfilling our nature as an intelligent, curious, expansive species. We explore because that's what intelligent beings do. We seek knowledge, experience, and new frontiers. Confining ourselves to one planet when the universe is vast and full of wonders would be a kind of resignation, a giving up on growth and possibility. There's also an ethical dimension. Earth is the only place in the universe we know for certain contains life. It's precious beyond measure, but it won't last forever. In about 1 billion years, the sun will gradually brighten, eventually making Earth too hot for complex life. In 5 billion years, it will expand into a red giant, likely consuming Earth entirely. Long before then, on timescales of tens or hundreds of millions of years, Earth will face other existential challenges. If intelligent life exists nowhere else, and we don't know that it does, then humanity and Earth's biosphere represent something cosmically unique and important. We have a responsibility not just to ourselves, but to life itself, to preserve and propagate it, to ensure it doesn't end when Earth becomes uninhabitable. This means eventually moving beyond Earth. Not because Earth isn't enough, but because nothing lasts forever. Then there's the simple fact that the universe is magnificent and worth exploring. The same impulse that led our ancestors to cross oceans, climb mountains, and venture into unknown territories drives us to explore space. We want to know what's out there. We want to see alien worlds, stand under alien skies, touch the soil of other planets. We want to know if we're alone or if life exists elsewhere. This desire for discovery and understanding is deeply human. It's led to most of our greatest achievements, scientific revolutions, technological breakthroughs, artistic masterpieces. A civilization that stops exploring, that becomes content with what it already knows, tends to stagnate. Exploration keeps us vital, engaged, and growing. But there's a counter-argument. Maybe we should focus on making Earth a paradise rather than expanding to other worlds. Maybe we should create sustainable civilization here, in harmony with our biosphere, rather than repeating the pattern of exploitation and expansion that's caused so much environmental damage. This is a fair point. We absolutely should be good stewards of Earth. We should address climate change, protect biodiversity, create sustainable economies, and ensure that all humans have access to food, water, healthcare, and opportunity. These aren't alternatives to space exploration, they're complementary. The resources and technology needed for space colonies can also help Earth. Solar power, recycling systems, efficient agriculture, sustainable manufacturing. All of these are necessary for space settlements and beneficial on Earth. The perspective gained from seeing Earth from space has been transformative, giving us a visceral understanding of our planet's fragility and beauty. The famous pale blue dot photograph, taken by Voyager 1 from beyond Neptune, has inspired countless people to care about Earth and its future. Moreover, the economic activity generated by space industries creates wealth that can be invested in solving Earth's problems. The Apollo program, despite its enormous cost, generated technological spin-offs worth many times its investment: integrated circuits, advanced materials, computer systems, medical technologies. Modern space industry is already contributing. Satellite communications, GPS navigation, Earth observation for agriculture and disaster response, weather forecasting, and more. So it's not space exploration versus fixing Earth. It's doing both because they reinforce each other. Another philosophical question: what gives us the right to colonize other worlds? This becomes especially acute if we find life elsewhere. Do we have the right to terraform Mars if there's native microbial life there, even if it's just in subsurface ice pockets? Do we have the right to alter alien ecosystems to suit our needs? Different ethical frameworks give different answers. A human-centered ethics might say that human flourishing is the highest value, and we should use whatever resources we need to ensure our survival and growth. A biocentric ethics might say that all life has intrinsic value, and we should minimize harm to other living systems. An ecocentric ethics might value entire ecosystems and argue we should preserve them in their natural state. There's no universally accepted answer, but here's a reasonable middle ground. We should explore carefully, study thoroughly before intervening, and preserve what we can. If we find complex life or ecosystems with intrinsic value and interest, we should protect them, setting aside preserves and studying them rather than destroying them. If we find simple microbial life, we should study it extensively. It could tell us about life's origins and possibilities, but might eventually use the resources carefully if we need them. If we find no life at all, as seems likely on most worlds, then the ethical concerns are less acute. A lifeless Mars has potential value as a scientific laboratory, as a frontier for human expansion, but not the intrinsic value of a living ecosystem. Terraforming it would be creating value rather than destroying it. In any case, we should proceed thoughtfully rather than recklessly. The universe is vast. We don't need to exploit every world we find. We can afford to be selective and respectful. There's also a question about what we're spreading. If we colonize the galaxy, what version of humanity and human civilization are we propagating? Our best qualities, creativity, compassion, curiosity, courage, or our worst, violence, exploitation, inequality, short-sightedness? Space colonies will likely develop their own cultures, adapted to their environments and circumstances. Martian colonies will face different challenges than orbital habitats, which will differ from generation ships, which will differ from colonies around other stars. Over centuries and millennia, these cultures might diverge significantly, becoming as different from each other as Earth cultures are today, or more so. This could be wonderful, a flourishing diversity of human and post-human cultures, each exploring different ways of living and organizing society. Or it could be concerning if some colonies develop in oppressive or destructive directions. We can't control how future societies evolve, but we can try to instill certain values: respect for life, commitment to knowledge and truth, compassion for suffering, humility in the face of uncertainty. If we embed these values deeply in the cultures we create, they might persist even as those cultures change and diversify. Another deep question: what's the ultimate goal? Let's say we succeed beyond our wildest dreams. Humanity spreads to thousands of worlds. We build a galactic civilization spanning millions of star systems with trillions or quadrillions of sentient beings. We develop technologies we can barely imagine. We persist for millions or billions of years. Then what? What's the point? This ventures into questions of meaning and purpose that have occupied philosophers and theologians for millennia. Different worldviews give different answers. From a religious perspective, perhaps the purpose is to fulfill a divine plan, to serve God's intentions for creation, to cultivate souls through growth and experience across the cosmos. From a humanistic perspective, perhaps the purpose is simply to flourish, to experience, create, love, learn, and help others do the same. The goal isn't some distant endpoint, but the journey itself, the richness and beauty of conscious experience. From a cosmological perspective, perhaps conscious beings play a role in the universe's evolution. Some speculate that intelligence and consciousness might be necessary for the universe to observe itself, collapse quantum possibilities into definite states, or even create the conditions for its own existence through time loops or quantum cosmology. These ideas are highly speculative but suggest that consciousness might not be a mere epiphenomenon, but something fundamentally important. Or perhaps there's no cosmic purpose, and we create our own meaning through our choices and values. We decide what matters: kindness, beauty, knowledge, justice, love, and work to realize those values as fully as we can. I find this last perspective most compelling. We're probably not fulfilling some predetermined cosmic plan. The universe doesn't owe us purpose. But that doesn't make our existence meaningless. It means we're free to create meaning, to decide what we value and work toward it. And there's something beautiful about the idea of consciousness, that mysterious property that allows the universe to experience itself, spreading across the cosmos. For billions of years, the universe was just matter and energy following physical laws, with no one to witness its beauty. Then life emerged, and eventually consciousness, creating pockets of experience and meaning. If we spread to the stars, we're expanding the realm of consciousness and experience. We're allowing more of the universe to be witnessed, appreciated, understood. We're creating more opportunities for joy, beauty, discovery, and connection. That seems like a worthwhile goal, even if it's not cosmically mandated. If you are still watching, make sure to subscribe to the channel. I am just starting this channel, and your support is the biggest fuel. It makes all the difference. Finally, there's the question of whether we'll remain recognizably human. Over the timescales involved in interstellar expansion, evolution will continue. Colonies on different worlds will adapt to different environments. Genetic engineering might accelerate and direct these changes. Merging with AI might fundamentally alter what we are. After 1 million years, our descendants might be as different from us as we are from early hominids. Is that concerning? It depends on your values. If you believe there's something essential about being human, something worth preserving unchanged, then radical transformation might seem like a loss. But if you see humanity as part of an ongoing evolutionary process, then transformation is natural and potentially desirable. Evolution on Earth has produced an extraordinary diversity of life from common ancestors. Perhaps the same will happen with intelligence. Human-descended civilizations might diversify into countless forms: biological, cybernetic, digital, forms we can't currently imagine, each adapted to different environments and pursuing different goals. Some might live as uploaded minds in vast computer networks. Some might genetically engineer themselves for life on high-gravity worlds. Some might become energy beings or distributed intelligences. Some might remain close to baseline human biology, either by choice or circumstance. If we value diversity, creativity, and exploration, this seems like a feature rather than a bug. We're not spreading a single fixed form, but unleashing a process of diversification and experimentation that could fill the galaxy with intelligence in countless forms. The key is ensuring that this diversification doesn't lead to conflict and destruction. We need ethical frameworks and values, respect for consciousness and life, willingness to cooperate, humility about our own limitations. That can persist even as forms change. Reaching the stars is hard. It might take centuries or millennia. It might require physics we don't yet understand. It might transform us into something we wouldn't currently recognize as human. There are no guarantees we'll succeed, but it's worth trying. The alternative, remaining confined to Earth, eventually declining and going extinct when Earth becomes uninhabitable, seems like a failure of imagination and will. We have the capacity to reach beyond our cradle. We have curiosity about what's out there. We have a responsibility to the only life we know for certain exists to preserve and propagate it. The universe is vast, ancient, and full of mysteries. We've barely begun to explore it. Every question we answer raises new questions. Every world we study reveals unexpected complexity. The more we learn, the more we realize how much we don't know. That's exciting. It means there's always more to discover, more to understand, more to experience. It means the future could be extraordinary if we have the wisdom and courage to pursue it. We're living at a unique moment when humanity is just beginning to become spacefaring, when we're taking our first tentative steps beyond our home world. Future generations might look back on this era with the same wonder and respect we have for the first explorers who ventured across oceans into the unknown. The stars are waiting. Whether we reach them in your lifetime or in the distant future of your descendants, the journey is worth taking, and in some small way, by thinking about these questions, learning about the science, supporting space exploration, and passing on the dream to the next generation, you're part of making it happen. The cosmos is magnificent. We're part of it, and one day, perhaps, we'll spread across it, bringing consciousness and meaning to worlds that have been dark and silent for billions of years. But here's the question we haven't answered. Using rockets we have right now, how long would it really take to reach Alpha Centauri? The real number is wild. Click the video on the screen to find out. The answer puts everything we just discussed into perspective.